The Nobel Prize in Chemistry was awarded for the discovery and synthesis of quantum dots. Physics is also interested in these little marvels, and they may have a big impact in quantum computing. Find out how quantum dots may take us to the million-qubit scale in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the CEO of SemiQon, Himadri Majumdar. Welcome to the show.
Thanks for having me.
Yeah. I want to have you on to talk about a few things, but before we get to the big point of this discussion that we start with, just give our listeners a quick sort of overview of how you found your way to quantum.
Sure. Glad to be here. And like you said, I'm now leading a spin-off from VTT Technical Research Center in Finland named SemiQon. We are the co-founders, started off as VTTers. So I have a long history at VTT, been there for 10 years in various different roles. I have a background in applied physics, so I did my PhD a long time ago, a couple of decades ago. And then after doing the due diligence in postdocs and all the other academic activities, ended up at VTT as a senior scientist first, leading multiple European and local projects, and then moved from science to sales. So I ended up leading the sales activities on microelectronics and the quantum technologies domain around 2015. And then having led that activity, being the head of sales, I jumped to the opportunity of leading the quantum activities when we sort of focused that part at VTT around when the pandemic started, basically around 2020. And then, so that was the role I was having there. Among other things, I led the project with IQM on building the first quantum computer in Finland. And that was a lot of fun. And while doing that, we realized that apart from doing superconductors and stuff like that, we will talk about it, but semiconductors was very, very interesting. And that ended up me being here today.
Yeah, and whenever I hear about like decades, because I've been around a while too, sure. I was wondering, were you interested in quantum way back, and then you finished and you're like, okay, there's nothing to do in quantum, so let me do this other stuff?
No, that's actually interesting because I started with nanotechnology, and at that time we were doing research on quantum dots, but for different applications. So quantum, as we know now, was not that prevalent at that time. So in that sense, I'm kind of a newcomer in quantum, so to speak.
So tell us a little bit about SemiQon. It's SemiQon, because we got to put a Q somewhere in a company name. So, sounds like semiconducting.
Yeah. We thought that would be the perfect merger of semiconductors and quantum. So that's where the name emerges. Like I said, SemiQon is a spin-off from VTT, and the idea behind the company is to build quantum processors or QPUs from quantum dots, semiconductor quantum dots. So silicon is our platform of choice. And the reason for that is we want to make sure that we can build quantum processors for the million-qubit era. Whatever the other modalities are doing now is fantastic and great because they are actually proving how important and useful quantum computing can be. But we will at some point reach the scalability plateau. And that's when we want to be ready with our platform that allows us to do it in a scalable and affordable way. So that's kind of like the long-term goal for SemiQon.
Yeah, we just had another company on with that same idea. I'm starting to see this more and more. Everyone's worried about how do we get more to like the million-qubit level. So it's definitely something that's on everyone's minds right now. It's the quantum zeitgeist, if you will. So normally on this show, we would expect to talk about the Nobel Prize in physics. That's the kind of thing that's come up. Last year, we had, entanglement. That was a big deal. And of course, the work had been going on for a while, Zeilinger, et cetera. But this year, it seems like the one of interest to my audience and my field is the Nobel Prize in Chemistry, which is a little strange. So the 2023 Nobel Prize in Chemistry was awarded for the discovery and development of quantum dots. So it's definitely something that's now buzzing about, and some people might not have even heard of it yet. I don't know if you want to maybe give a little mini tutorial on what quantum dots are and explain them to our listeners.
Yeah, absolutely. And this whole domain of quantum dots, like I said, was fascinating about a couple of decades ago already. And that's when the original works were done. And the reason it's the Nobel Prize was in chemistry was because they were given for finding quantum dots. Quantum dots, first of all, is particles, very, very small particles with the radius or diameter of 2 to 10 nanometers. So they were discovered in colloid suspension, so in liquid forms. And that was kind of like the starting point when we could see fascinating things happening in liquid. So we could have colors out of liquid when you shine them. So just because they could excite them to a certain energy level and you could emit, and that emitted the light. So it was fantastic things at that time. And then slowly we saw the emergence of quantum dots in more, let's say, solid state form. So that's when we started seeing television having quantum dots in them and things like that. So it's absolutely fantastic how you can find new ways of doing physics, even though it emerged out of chemistry, but you can do physics, fascinating physics in those dimensions. And what we are doing, for example, is we are using something called single electron transistors. And that's kind of like a quantum dot territory where we want to confine electron in a dot and then manipulate it using, let's say, electrical and other pulses or magnetic pulses to use them as qubits. So the journey actually started long ago where you can confine electrons in a dot-like space in that few nanometer space. And now we are actually utilizing it to build technologies around it.
Yeah, so it makes sense. With the Nobel Committee, they were just like, oh, we found it in liquid, give it to the chemistry guys. Yeah, that makes sense. But like you said, yeah, it has big implications for us. So what are some of the benefits to using this approach, that single electron, the quantum dot, to manufacture a QPU? What makes it better? Basically, we could zoom in a little bit.
Yeah, sure. So why we chose this or we wanted to explore this option was there are two aspects. First of all, the idea of confining electrons or holes in a dot and then manipulating it is a very elegant way of doing computing. Obviously, there are challenges with multiple different aspects there, but the idea of it is very elegant. And then the second aspect, which is more on the commercial side, is the semiconductor technology by itself is now reaching a very, very interesting phase. We are even talking about 2 nanometer dimension of semiconductor transistors, and they are going to be commercialized very soon as well. So the semiconductor industry is coming to the point through Moore's law and developments as such, where it's reaching that quantum boundary, so to speak. So the whole process that the semiconductor industry went through in manufacturing these kind of devices is already known. And we all know how Moore's law helped, or according to Moore's law and how it worked, that we could scale up the volume in small space. And our approach is, why don't we take it from the quantum angle and do the sort of device structure, design, everything that is suitable for building qubits, but use the manufacturing understanding at the same time, so that when it comes to scaling, we can not spend too much time reinventing the wheel. We can just go the way it went with the semiconductor industry. So those are the two factors that drove us to this direction.
Yeah, because we've already done this. You're basically saying, right? We've already scaled
Exactly.
this general approach.
Exactly.
But of course, when you did that, you didn't have to worry so much about the universe making observations of your qubit and things like
Mhm.
that. So one of the steps, I guess, towards this is this approach of integrated cryogenic control circuitry. So if you want to talk a little bit
Correct.
about that, how you make this whole thing work together.
Yeah, sure. So yeah, you are absolutely right that one aspect of it is the qubit when we talk about quantum dots, but there is a lot of control electronics and a lot of manipulation that is needed to get the information out of those quantum dots or qubits as well. And I cannot tell too much of details due to obvious reasons, but what I can say in a general way is if we look at a quantum computer that exists now, the first thing that you see is obviously the cryostat. That's the shiny fridge, expensive fridge there. But you also see a lots of cables going in, and they are the ones which are used to read and control the qubits. And the more we go into a higher number of qubits, the more we are expected to see those kind of cables and electronics there. And what we are saying is, obviously, we have the quantum dots and the qubits on the chip, in silicon chip, but silicon also offers us the opportunity to create circuits, to create switches or any other components that is needed to replace some of these cables. So that's our approach. So what about, instead of bringing in cables, we do the electronics on the chip, at the same chip where we have the quantum dots, and do the control using those. So there, the novelty is that you have to make the chips operate at very low temperatures. So that's the Cryo-cmos, where it comes from. The initial idea would be to replace some of the cables. We still would need some cables, but eventually we would try to go to what we call a quantum IC domain. So it would be a qubit and the control electronics all on the same chip.
We'll talk a little bit about error correction later, but was there any goal given to like a size of how many ideally you'd want in one module going forward?
We are still looking at it. We have to see how densely we can pack them together. It's a design challenge as well, not just fabrication and measurement. But what we can definitely say is we can densely pack a lot more that we are seeing now with other modalities in the same footprint. So that we can definitely assure.
Okay. What temperature range do these operate within, these qubits?
That's a very good question. So, because therein lies another potential advantage as well. So, what we are doing now is we are operating in hundreds of millikelvins. So, just as a reference, that's about 100 times more than where, for example, the superconducting regime is. And what we would like to do is take it to the Kelvin range, so the space temperature range of 1 to 5 Kelvin. And that allows us not just to be 1,000-fold more efficient in a way, but from a technical perspective, this gives us a bit more energy freedom to actually use them for not cooling, but use them for manipulating and controlling the qubit. So that's another advantage of having this. So hopefully hundreds of qubits soon, hundreds of millikelvins right now, but then going into Kelvin range.
So if you get it to 1 to 5, then you can just float it in space. You wouldn't have to pay for cooling at all.
Yeah, exactly. Wouldn't that be fun? But yeah, I mean, that brings down the cost of cryogenics significantly as well.
Yeah, people don't realize how crazy it gets when you get to the millikelvin range.
Exactly.
It's literally the coldest place in the universe. It's colder than deep space, colder than anywhere else. So it's wild that we can point to the coldest place in the universe. It's right here on Earth. So how does this general architecture affect scalability then? I mean, you kind of hinted at this, but are there any other like plans to make these things like work together, have chips like connect to each other?
Yeah, well, many different options to look into. So first of all, we want to see how much we get on a single chip. And then the design rules and how good we get entangled, not just the near qubits, but the far qubits as well, whether it's a 1D array or a 2D array and those kind of aspects. that will define the first, let's say, set of architecture. And then the second set is whether we go 2D with the architecture or we go 3D. So we sort of tandemly stack up chips, or do we just expand on the sideways? There are challenges in everything in that respect. So the idea is to, or let's say the overall goal is to reduce the footprint. So would like to compact it as much as possible without losing the efficiency of the qubits. But other than that, it's still quite wide open how it will be done.
Okay. And do you anticipate needing the qubits to be very close together at all?
They have to be. I mean, it's a kind of from a very general perspective. You want them to be close enough to talk to each other, but you don't want what scientists call crosstalks.
Crosstalk, yeah.
So it's a double-edged sword in a way.
Yeah, and if you think crosstalk's bad in regular electronics, here you might be having crosstalk from other dimensions, right? From other parallel worlds. So, that's even worse.
Exactly.
Infinite amount of crosstalk.
Yeah, exactly.
Yeah. I stick Everettian physics into this whenever I can. So that seemed like an opening. So what other barriers to fault-tolerant quantum computing do you see? And how do we overcome them?
Yeah, well, that's a very sort of challenging question, because fault-tolerant quantum computing is something that we all are hoping for, but it's a very, very challenging aspect. So, for example, when Google came up with the Sycamore, and then they sort of thought about or hypothesized that how much you need, it was the need was one error in 10 to the power 6 or 10 to the power 9. And that's crazy, because from a manufacturing and fabrication perspective, that's very, very stringent requirement. And it's hard to get there. But it's the way it's going to happen is we will see a lot of quantum error correction. So we will see a era where to get a one logical qubit, we would need to have multiple physical qubits, which will keep or have the error correction, and that will help us to get to that point. But there is also the other aspect of repetition codes, or how we do the coding, because that also defines how we can build better processors. So from that perspective, there are obviously issues like noise coming from manufacturing, noise coming from defects, and other places as well. I mean, we are talking about dimensions of few nanometers, so that's absolutely impossible to operate if you have, for example, a speck of dust that ruins everything. So we cannot even think of those things. So all these things taken into account, even though we achieve or thrive to get to the fault-tolerant quantum computing or general-purpose quantum computing, we are still quite far away from that because of the challenges that I mentioned. And the other aspect is also how you do the codes, how you do the readouts, how you do the electronics. They all add up. So it's a community task to get the problems to be solved, rather than a problem for a company like us. We cannot ourselves handle that question.
Okay. Do you see this technology being used only in a QPU, or do you think that because if it's not that cold, et cetera, do you think that this could be something for something like an ASIC, like let's say a right. repeater for a communications network or something like that?
Yeah, those are potential applications. So obviously, as a company, our goal is to stay focused on the QPU, but there are what we call side streams as well. So there will be potential opportunities, like we discussed about CMOS or Cryo-cmos, that can be of interest for other modalities as well. So not just for us. But so there can be various different. I won't go into that because there are business opportunities in those cases that I don't want to divulge. But yes, in principle, there can be multiple different short-term benefits for doing this.
And is there anything, just also thinking along those lines, is there anything about quantum dots that makes them useful for like a sensing application or
Of course
anything?
they do. Yes, a topic which is already under heavy investigation.
So I won't probe too much there. I could
Sorry
sense
about
that
that.
there are
We will.
nervous
We
folks
will.
listening, going, "No, he can't talk about our deal that we have under." Yeah, okay. So getting back to QPUs, how soon do you think we would expect to see a QPU from SemiQon?
Hopefully soon. So what we are currently doing is obviously working on our first generation of QPUs. They will not be, or let's put it this way, we will be competitive from a global perspective, and that's what we want to do. But since we are a QPU maker, we rely on certain measurables or KPIs for the QPU itself. So we don't build a full stack quantum computer. So if anybody wants to know how will our QPU work in a quantum computer, then I would say there has to be a bit of wait, because we know that this is a challenge, and for that reason we paired up with a company in Netherlands, and we have a joint project currently ongoing where we will build the QPU and they will do the system integration in a full stack demonstrator of a quantum computer with that. So by 2026, we should have the first demonstrator of a full stack quantum computer with our QPU. That's at least the plan for now, but who knows? I mean, things can go even quicker. We'll see.
And I know you kind of refer to it as like the first Finland like quantum computer, right?
No, that I think that accolade has already been taken by IQM and VTT when they built it with
Yeah.
the superconducting platform.
Mm-hmm.
So that has already been demonstrated. But from a spin qubit perspective with semiconductors, that's still ongoing, let's say.
Okay. And would this then be put to some kind of, is there any kind of like government partnership or anything happening? Are they interested in like using it?
That's a very good question. We hope there will be, because I think with any new technologies or any new breakthroughs, there has to be some sort of government programs or government procurement, so to speak. So we hope that there will be opportunities like that as well. The interesting bit is that the way the quantum computing is evolving now is through integration with high performance computing or supercomputing centers. So that would be one way of adding value to those HPC centers by quantum. So hopefully spin qubit will also have an opportunity to get to that direction as well.
So around 2026, maybe this QPU is integrated into something. Did you give any thought to like a roadmap from there? Like how does that go down to 2030, for example? Like what numbers?
Of course. I mean, now, like I said in the beginning, all the modalities, including us, we are already, let's say, not that advanced. But with all the other modalities, we are talking about hundreds, even perhaps 1,000 at most. But that is not where we are. Where it gets interesting. It gets interesting when you get to 100,000 and plus with the physical qubits, so that we can get error-corrected qubits as well from them. But the goal for us is, as a company, we want to reach thousands of qubit or 1,000 qubit by end of this decade. And then what we hope to achieve is something in the equivalent of Moore's law, where we can actually double hopefully every year, the qubit count. And that takes us to 1 million by 2040. So that's our kind of goal at this point of time. And we have to keep it in mind that other modalities might get close to that as well before us. But the issue there will be, will those be scalable solutions that are deployable at an affordable price? And that question, I think, is still very open. Our goal is to make it scalable and affordable based on everything that we are doing.
It's interesting you said Moore's law because while you might achieve something like doubling a qubit count, you're doing way better than that in performance because every time you add a qubit, it's literally doubling the addressable information states.
Hopefully with logical qubits, yes.
Yeah. So you're doing way better than Moore's law technically if you achieve Moore's law in numbers. And on that note of like performance, do you have any idea of fidelity, what we're looking at for these qubits?
Like I mentioned in one of your previous questions, the fidelity expectation are very, very high. And what we are trying to figure out is how we can strike a balance between scalability and the efficiency, let's say, not just fidelity, but all the other measures as well. And this is a constant discussion within the community that how do we approach that? Do we have error correction mechanisms, or do we do it the NISQ way, where we have a lot of physical qubits, which kind of allows us to get better logical qubits? And our approach at this moment of time is more on that side, on a brute force kind of, if you may call it that way, that we want to increase the qubit numbers so that at the end of the day, we get sufficient number of logical qubit out of that system. And then comes obviously the question of what are the fidelities, what are the sort of computation capabilities. That remains to be seen. So we still don't know. Obviously, we target the best we can, but there is a balance between performance and scalability or volume in that sense.
Yeah, what no one ever seems to be able to really share is how do you go from understanding your fidelity to understanding what your estimate of a logical qubit is, right? That ratio.
Right.
Because IBM said 1,000, right? 1,001. Where'd they get that from? Did they do it based on some calculation they didn't share about the fidelity times some factor? Or I don't know if you had any thoughts on that, like what it would take to figure out that ratio.
That part we actually rely on the quantum information scientists. So they have to tell us what are the potential let's say codes that they can write on the qubits that are given and how they can get the information out. So we don't know exact numbers from that perspective. So it depends on the errors come from the architecture. It's also coming from the hardware, the process, and everything. So all the errors add up. So IBM's guess or IBM's statement of 1,000 qubit is as good as anything. So we will see. We can tell better when we can use our physical qubits to get to a logical qubit. So then we are wiser that how many we need to do that.
Because you did it.
Now, 1,000 sounds like a reasonable number. Yes.
Okay. And just, I guess, one last point. So this is Quantum Dot, and there are other companies obviously looking at this, and Intel's a good example.
Yeah.
They have their quantum development SDK. So when it comes time to make this full stack, do you envision maybe leveraging something like an Intel SDK and just making this another backend target, or do you plan on like maybe just pushing for a completely new stack all the way up?
That's an excellent question because, as like I said, we want to leverage the existing know-how and existing technology in semiconductors, right? So from that perspective, it would make sense to rely on a bigger player to define those aspects. But having said that, there are certain challenges when it comes to designing quantum dots or QPUs, and they come from the stack itself. So without going into details, I can say that the idea that we can take the current semiconductor or current transistors and hope that they will work as quantum dots is challenging. So we are taking a more bottom-up approach in that sense. So we define the stack which is best suitable for building QPUs. And from that perspective, we might not be able to use the PDKs or SDKs that are available already. So we might have to tweak some of those to some extent. And then the question comes that, are we doing it in an industrially scalable way? Yes, we are. But that needs to be adapted to a larger foundry when the volume gets to that point. So this is another aspect which not just us, but our competitors are also looking at, that what are the opportunities that there is and how we can take advantage of the existing SDKs and PDKs. But it's not clear yet how it will go.
So when something like this Nobel Prize happens, does it instantly open more doors? Does it make conversations go more smoothly? I just wonder if behind the scenes, when a company's involved with their modality and something that gets that kind of attention, does it become a yes moment, like you're ready to take advantage of that?
Obviously it does. You have to ask that question to a marketing manager and they will be like, yes, of course it is. No, but being in that field for long enough, you would guess that, yeah, that is obvious. That is inevitable. It's bound to happen. It was the same thing the last year's Nobel Prize as well. We were all happy that it happened. But I think at the end of the day, Nobel Prize just makes it visible to the community and helps us get a wider audience for what we are saying. But the challenge remains the same. So in a way, it's a good thing that everybody's understanding and learning about this thing. But it's also a challenge because the expectations go up as well. So it's good and bad, but we want to look at it from the good perspective.
Well said. Thank you, sir. And with that, I'll wish you best of luck in reaching those timeline goals. Thank you.
Thank you so much. Thank you for having me again.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today in case things got too nerdy at times. Let's recap. The 2023 Nobel Prize in Chemistry was awarded for discovering and synthesizing quantum dots. These are 2 to 10 nanometer particles with properties that change based on size and quantum phenomena. For example, their color changes based on size, leading to their use in QLED screens. Quantum dots are also used in single electron transistors that can be manipulated with magnetic fields or voltage pulses to work as qubits, where the electron spin states act as a 0 or 1. Quantum dots can be manufactured in large quantities with precise control over their size and properties. This elegant way of manufacturing makes them ideal for building large-scale quantum computers, and it may be possible to stack qubits 2 or 3 layers deep. The hope is to scale based on pre-existing fabrication knowledge and reduce the overall footprint. SemiQon is also working on controlling these qubits without the wires and cables used in other modalities like transmon. The hope is to have control circuitry that operates at low temperatures right on the chip, called Cryo-cmos. And the temperature is warmer than those other modalities too. Quantum dots operate in hundreds of millikelvins and may stay coherent in single-digit Kelvin one day. That's 1,000 times warmer than transmon if the approach works out, lowering cooling costs and potentially improving performance. SemiQon might be able to use Cryo-cmos for other devices and is considering implementing quantum dots in other devices too, perhaps in quantum networking or sensing. The first generation of SemiQon QPUs in a complete system should appear around 2026. They hope to achieve a Moore's law-like doubling after that, yearly, to scale into thousands and millions of qubits. That does it for this episode. Thanks to Himadri Majumdar for joining to discuss SemiQon. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker, that's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.